got our next speaker about your game will suck without zero knowledge proofs. Do we have Frank from Aleo? Hey, hello, welcome to the stage. Round of applause for Frank. Come on up, come on up. There's your clicker.
Thank you very much.
Yeah, we'll take questions at the end.
All right. Can you guys hear me through this thingy I got in my ear? All right, awesome. So my talk today is your game will suck without zero knowledge proofs. My name is Frank. I'm a product lead at Aleo, which is a decentralized zero knowledge layer 1. So obviously we're going to be implicitly talking about blockchain games today, where some state of the game is stored on a public distributed ledger. The first thing that comes to mind when I use blockchain and gaming is going to be why decentralized gaming? And to answer that question, I generally like to back out even more and ask why decentralize anything? The answer that you'll usually get is that it's to remove the need for trusted third parties. And we can sort of go through this with an example with how Bitcoin solved the double spend problem through putting money on a distributed immutable append-only ledger, which removes the need eventually for third-party financial providers. And analogously, we can do the same with decentralized gaming if we get it right, and we remove the need for centralized gaming services, platforms, and marketplaces. Now, it's interesting because it's not catastrophic to society if we don't get that right. And arguably, if we look at the other side of the argument, these centralized services, marketplaces, and platforms that we use for gaming have made our games better. They actually help coordinate these games and also ensure fairness. So the problem is trusted third parties can and eventually will steal, surveil, and limit your use. So if we look at money as an example, they may steal your money and appropriate it. They may steal by devaluation and inflation. They may sell your data without consent for profit, or they might limit you, lock you in, censor you, and deny you services. Same thing with the gaming industry. In the gaming world, they can steal your assets and basically rug pull you, stop the game and basically disallow you to play it. They can steal by printing or minting, so the assets that you already own in your game are going to be worth a lot less. They can also surveil you. So the game is a product, but I think with many products, you are also the product. Your data is the product. And then you can, like I said before, lose access at any point. So the way that I like to answer that question at the very end is decentralized gaming is a better investment of time for everyone. So if we can make stealing, surveilling, rug pulls much harder, we don't outsource trust to these entities, and that boils down to protecting your investment as protecting your investment of time as a gamer, because you protect the value of the assets you own, and you get greater value when you're playing peer-to-peer. On the other side of the market, you can also experience a lot more transparency for those who are making games, and then these are all things that just help prevent a catastrophic exit stage left for the entire gaming industry. So we didn't really talk about like how we're going to do this. And so like the whole point of my talk is why do these decentralized games suck? So we can go through like a simple chess example that's on the blockchain. So Alice and Bob commit to playing this chess game. They're essentially going to have a stakes of 1 Bitcoin. So whoever wins the game will earn a Bitcoin. Whoever loses the game will lose a Bitcoin. And they're essentially broadcasting their moves on the blockchain. These are all moves in plain text, and everyone in the network can validate their execution, and these moves are being broadcasted to the blockchain. Any node in the blockchain is then able to validate that those moves execute correctly. And this is the good thing about blockchain games, is that everything is public, distributed, and so anyone can check everyone else's work. And it's also good because we can see that if Alice decides to try and do an illegal move, any node in the blockchain network is able to check that execution, and it's Alice's execution and computation that will not align with anyone else's, and therefore she won't have consensus. and therefore the blockchain can see this and basically programmatically pay out to Bob. This is the same thing if Alice tries to do a take-back move. The blockchain is eventually able to see this and programmatically pay out to Bob. So why does this suck? I think chess is a relatively simple example. But if we start looking at very, very large, massive multiplayer games, it just simply doesn't scale. There's like way too much computation going on. There's no privacy, and we'll come back to this point because it's very, very important. There's no privacy because chess is a perfect information game, so all of the players are aware of the game state at any given time. And this changes when we start talking about imperfect information games. The only good thing remaining here is that there's trustless execution, so anybody can compute the moves that were made by Alice and Bob in this game and confirm that they were indeed following the game state. So going back to the privacy point, perfect information games are games in which all the information about the game state is available to every player. That includes chess, that includes checkers, that includes Go. Problem is, these aren't the only games that I want to play on the blockchain. And so in these cases, privacy is not really needed. So imperfect information games is kind of like all the other fun stuff that I kind of want to play. And so these are card games, these are real-time strategy games, first-person shooters, massive online battle arena games. And this is games in which all the information about the game state may not be available to every player. Because if the game state is public, something like these moves that you'll make in a real-time strategy game are going to be shown to basically all of your opponents. So like Texas Hold'em wouldn't be much fun if I could see all of my opponent's cards. It wouldn't really be much of a card game. And then me sending like a flanking team in a real-time strategy game or a first-person shooter game wouldn't be much of a surprise to the enemy either, because they know what I'm doing just by looking on the public ledger. And so this is why we need trusted third parties to coordinate the game state and to keep it private, kind of like a God's eye. And so, like I said, player privacy is the problem that we have to solve, and that's the reason why we need trusted third parties for online gaming. How are we going to do that? There are a variety of solutions out there today. There are trusted execution environments, fully homomorphic encryption, commit and reveal schemes, and then there are zero-knowledge proofs. I'll go through each of these pretty quickly and just like give an overview of like where the pros and the cons are. So a trusted execution environment is essentially a physical computational device that is impossible for someone with access to the hardware itself to know what it is computing. Why does this suck as a solution? It doesn't scale. Not everyone can execute it. It requires the right type of environments. There's deployment complexity. There's special hardware that's needed. In the news as of late, there have been a lot of side channel attacks, so your privacy can be compromised, so it's not fully private. And then lastly, it's not exactly trustless execution, because if you trace back the hardware device that you're using, you're trusting the entity who made the hardware device to not have tampered with it. And so it's not exactly trustless. In fully homomorphic encryption, this is an encryption scheme that allows for encrypted code to be computed on as if it wasn't encrypted. So as an example is if you're encrypting critical game data, such as player inputs and game states, and then you're performing computations on the encrypted data, it becomes much more difficult for cheaters to manipulate or exploit the game. This is obviously to help maintain a fair and secure gaming environment. Why does this suck? It really doesn't scale. It's essentially a trusted execution environment that's built out of math. And so you have cryptographic guarantees of its security, but you're essentially running computations on encrypted data, which is a lot of computation. The good things about it is that it's private and it's trustless execution. So anyone who has the computational power can run those computations. Commit and reveal schemes are essentially, we'll go through an example of this, but it's similar to like with the chess game, but instead you're hashing your movements on a board and you're committing those to the blockchain. And then at the very end, you will reveal all of the moves that you have made at the very end. And so execution verification is performed optimistically at the very end of the game. So we'll go through an example of this. So instead of chess, we're playing StarCraft now. As an example, Alice, in her 5th move, decides to purchase 2 Brood Lords. We're going to put that into a hash function so that when we do put that movement onto a public ledger, Bob is not going to know what that, Bob or anyone else in the network is not going to know what that move actually is. And so the blockchain and the participants in the network don't know what that move is. Similarly, Bob can do the same thing. Like he'll hash the movements that he does within the game and push that to the blockchain, but no one actually knows what Bob did until the very end, where we do essentially the reveal of all of the secrets and the witnesses that they pushed on the blockchain. And once this happens, the game state is revealed, so all of the participants in the network can agree that, yes, Alice did indeed buy 2 Brood Lords, and Bob somehow still managed to destroy their opponent's base. So what's the problem with this? It still doesn't scale well. There's more computing hashing going on. There's more block space for storage, and then there's also more communication and overhead. There's no incremental verification, and what do I mean by that? It's kind of like you're trusting a bunch of moves until, like, you're trusting a block of moves until the very end of the game. And so at no point during the game can I actually know that Alice or Bob is cheating during the game. And then it's not private after the reveal, which is a big thing. So let's say like Alice had a game-winning strategy against Bob, and Alice is a pro gamer, and she wants to use that strategy on Charlie next week. But the problem is, if she plays this blockchain game and you have to reveal all of your moves at the very end, her game-winning strategy is revealed to Bob and everyone else in the world and anyone else participating in the network, and therefore her strategy is basically revealed and she can't use it against Charlie anymore. So there's limited privacy after the reveal. And then again, there's trustless execution. Anyone with that kind of computing power can perform all the computational executions necessary to find out that the game state did play out the way that it did play out. So the last solution is zero-knowledge proofs. Zero-knowledge proofs are essentially that I can prove to you that I know a secret without revealing what that secret is. That's my very simple definition of zero-knowledge proofs. And so usually there's going to be 2 parties when we're using zero-knowledge proofs. There's going to be a prover and a verifier. And so the prover can take inputs and create an arbitrary amount of computation on that input and basically create a cryptographic short proof that's quick to verify, and they can choose to conceal or reveal anything about that computation. And then they give that proof to a verifier who can prove the execution and basically know that the prover knows a secret without actually being told anything about that secret. So if we go back to our example with StarCraft, we can play out the same scenario using a ZK snark, which is a type of ZK proof. So when Alice has move 5, she purchases 2 Brood Lords. This time she hashes it and hashes that like change in the game state along with a zero-knowledge proof that states that it's a valid game state transition. So now Bob can run this proof and know that cryptographically Alice is playing the game within rules, and that, for example, she has purchased items, but he will know nothing about those items. He just knows that Alice is playing within the game rules. And similarly, Bob can do the same thing. Bob can generate a cryptographic proof with private inputs about a new game state, which is destroying Alice's last base. Alice can run this proof and know that cryptographically Bob is playing the game within rules and that he has manipulated game state in a way that he has won without actually revealing anything about his strategy. So why does this suck, or why does this not suck? It's scalable because the computations can be run off-chain. There's incremental verification, so we're not waiting until the very end of the game to actually figure out like whether or not those moves were valid and within rules. And it's also private because that's the nature of a zero-knowledge proof. I'm constructing cryptographic math stating that I know a secret and I don't need to reveal that secret, but I can still prove to you that I am within bounds on a game. And then there's trustless execution. Anyone can run these proofs given that they have the computational power. So this is really the only way to do decentralized gaming if you don't want like third-party actors who used to coordinate privacy and game states for us. And I also argue that this is the only way to really decentralize anything with privacy as a default. So then the question becomes, what combines the privacy necessary for these kind of imperfect information games with the programmability of something like Ethereum, and then the scalability for a good experience on the client side? And that's Aleo. Aleo stands for Autonomous Ledger Execution Offline. And essentially it's a decentralized, or it's a platform to build decentralized and private applications. You can think of it as kind of like the privacy of Zcash, the programmability of Ethereum, and also the scalability, compressibility, and privacy of zero-knowledge proofs all rolled up into one. In order to do that, we basically had to build everything from the ground up. So just to give a quick overview, we have a new ZK execution model called Zexy. We have a new ZK snark proof system, which is a combination of Marlin and Plonk. A new consensus mechanism, which is a proof of work, proof of stake hybrid, and then a new ZK domain-specific language. So it's like a language abstracted enough that can formally compile to a ZK circuit. We paired up with a dev shop called Crya, and they're helping us to build an open source ZK gaming toolkit, so to make developer lives easier when they want to come and build decentralized private games with us. This toolkit is open source, and we definitely want the community to come and help us build it as well. We've used this toolkit to build our own ZK game called Bologna. It's essentially like a version of Liar's Dice, so if you have time, you can visit that and sort of take a look and play. We did release the first version of it just about a month ago, and so we're sort of going through our second iteration for improvements, both on the game and also the open source gaming toolkit. You can also check us out. We have all of the poker tables hosted in the other room, so you can come and learn more about Aleo there. And before I think I have a couple of minutes, I just want to have a quick summary about some of the points I talked about, just like some takeaways I want you guys to know before I leave. So why decentralized gaming? Decentralized gaming is a better investment of time for everyone. If we make stealing, surveilling, and rug pulls harder, that means the people who decide to do gaming, we get to protect the assets that they own, we get greater value when we're playing peer-to-peer, and then we experience things like transparency instead of censorship. The problem in decentralized gaming right now is player privacy, and this is why we need trusted third parties for online gaming. So if we can solve player privacy, then we can have a better decentralized gaming experience. Zero-knowledge proofs is one of the ways that we can do that. And to me, it makes the most sense in these categories. So it's scalable, it has incremental verification, it's private, and has trustless execution. And that's Aleo. You can come to our platform and build your decentralized private applications. And this is where you can find us, aleo.org. Aleo HQ on Twitter, Aleo Systems on YouTube. I am product lead for consumer products, so happy to talk about how ZK can also be applied elsewhere and not just gaming. Special thanks to Sam Parker. He was our gaming lead, and unfortunately he couldn't be here today, but I learned a lot from him in terms of ZK gaming. And then Crya is the dev shop that we've been working with for the ZK gaming toolkit. That's it. Thank you.
Thank you. Great, really interesting. And I know, Frank, you're going to join us for the panel as well, aren't you? So
yes,
we can talk a little bit more about that then. But we've got a couple of minutes, so if anyone has any questions directly for Frank before we go into the panel, please do.
That's a good question. Is the SDK ready already? Sorry.
Yes, I believe you can start playing with it. Yeah.
Oh, okay.
Yeah. So if you go up and go to the booth at Aleo and provide like your email address or whatever, we'll be sending out an email with all the resources and stuff to get people started. Yeah.
That's good, because one of the questions I was going to say is it hard for developers who are just getting into Web3 to implement?
I think that's the whole point of the zero knowledge domain specific language that we've written. It's like very similar to Rust, and the whole point is it's almost like an onboarding platform. It's like we don't want people to be focused on their inability, or it's just very hard to make ZK circuits out of. It's really hard to just understand cryptography in general, and we want to make that easier. So you go through the language and you write a program, and we're able to compile those into ZK circuits for you.
That's great. And the explanation you gave earlier on with the chess games and the various explanations how that works was great. And if anyone came in after that and missed that, I should say we're recording this, so people will be able to watch it back. Any other questions for Frank before we move on?
Right here in the front.
Oh, okay, great. Yeah, sorry.
I don't know if this is really a question, but it just seems like using blockchain technology, it seems like it's able to eliminate like a lot of issues of like traditional gaming in terms of like in online like cheating. It seems like this is like a solution to a problem that has kind of always existed.
Yeah, I think like it does eliminate cheating, but again, like if you don't do it in a privacy preserving way, like you can eliminate cheating, but then if everything about the players and all their assets and inputs are basically exposed, it's just like a very limited set of games that you can actually build and successfully play on blockchain. There's a whole host of other problems with decentralized gaming, and we might get into that into the panel, but yeah, totally agree with you. Mm-hmm.
Well, that's great. Do you know, that's perfect time. So another round of applause for Frank there, and we'll move on to our panel. Thank you.